Hi there, this is part 2 of our video on transformations and operations with functions. So in this video, we're going to talk about the different operations we can do with functions. So we can add them. So if we have 2 or more functions, you can always add them, subtract them, multiply them, divide them. With dividing, just make a mental note that once you divide 2 functions, your domain, right, is going to be, you have to eliminate the values of g that make the function 0 from the domain. And then the other operation that we can do with functions is compositions. But let's look at this example. Let f of x be 2x plus 1 and g of x be x cubed minus 1. So part A is having us find f minus g of x. So this will be a pretty standard notation that you'll see, f minus g in parentheses and then of x, right? Because the way that you read a function is f of x, 2x plus 1. So this will be f minus g of x. So what this means is essentially f of x minus g of x. And so we look at what is f of x? Well, f of x is 2x plus 1 minus g of x. Now g of x is a binomial, so more than one term. So I'm going to make use of my parentheses just because I don't want to forget to distribute that negative. So I'm going to say, okay, now let's do that distribution. As I mentioned in one of the prior videos, if you're really good at keeping track of that negative and distributing as you go, then you don't have to use parentheses, but most of us tend to forget to distribute that negative, so just put parentheses in there when you see that it's something more than a single term function that you're subtracting. So 2x plus 1 minus x cubed and then plus 1. And then combine like terms if there are any. So in this case, and try to write them in descending order. So I'm going to have x cubed, negative x cubed, plus 2x, and then the only like terms are the plus 1 and plus 1. So notice that those did not cancel, right? Because that negative is distributed. So minus and minus becomes a plus. So I'm going to have plus 2. And so this will be my f minus g function. So I can write f minus g of x is equal to negative x cubed plus 2x plus 2. As you're doing your homework, if you're off by a constant, just make sure that you, if there were any subtractions, that you made sure to distribute that negative. Right, what about the next one? Oh, and find the domain. So the domain, both of these are polynomials, so f and g on their own have all real numbers, right? So the domain of f is all real numbers, and same as the domain of g is all real numbers. So together, we're just subtracting them, so the domain is, notice that this function is still a polynomial, so the domain is still all real numbers. Now, what about part B? Find f divided by g of x. So that means find f of x over g of x. So f of x we know is 2x plus 1, and g of x is x cubed minus 1. And can we simplify this? Not really, right? Not in the sense of canceling things out. So this will be our function. But now how do we find the domain? We did introduce a denominator, so for the domain, we want to exclude any x values where the denominator is 0, where x cubed minus 1 is equal to 0. So that means you gotta solve that equation. So solve x cubed minus 1 equals 0. This is a cubic, so what are our cubic factoring formulas? We may have forgotten them, we may have them handy in our memory, so wherever we are, let's remind ourselves, x cubed, when you have minus a cubed, this factors into x minus a, and then x squared plus xa, and then plus a squared. And then when you have x cubed plus a cubed, this factors into, what does that factor into? x plus a, then x squared minus x times a plus a squared. Usually you see it more as like your a cubed minus b cubed and a cubed plus b cubed. I don't know why I wrote them with the x's, probably because that's what we have here. So in this case, x cubed minus 1, then this looks like the x cubed minus a cubic. So then this is going to factor into x minus 1 times x squared plus x times a. A is 1, so just x, and then plus a squared. A is 1, so just plus 1 equals 0. And so I know from this one, x minus 1 equals 0, or in the other term gives me x squared plus x plus 1 is 0. So here I get x equals 1, and here now I have a quadratic, and I have to see if it factors, and if it doesn't factor, can I use the quadratic formula? So two numbers that multiply to 1 and add up to 1, that's not going to happen. So this, I'm going to guess that it doesn't have any real roots, and you can quickly check the discriminant to see. The discriminant is the b squared minus 4ac from the quadratic formula. So you have a is 1, b is 1, c is 1, everything is 1. So the discriminant says 1 squared minus 4ac. So you're going to have -3. So that's what's in the, when you have the quadratic formula, right? The b squared minus 4ac is what's inside the radical. So inside the radical, you can have -3. So this has no real solution. So we don't get any zeros from that. So that means that the only thing that's not in the domain is 1. So the domain of this function, now that we have it, so putting it all together, f of x or g of x was 2x plus 1 or x cubed minus 1 with domain all real numbers except 1. So that means it's going to be -infinity to 1, not included, union 1 not included, all the way to infinity. So the only thing that we're not including is 1. All right, so that's how we deal with things like this. If you're adding, subtracting, multiplying polynomials, chances are the domain is going to stay the same, all real numbers. It's really when you start dividing them, that you're going to have to work a little more to find the domain. So whenever you introduce that denominator in the domain, you want to exclude the values that make the denominator 0. All right, so those are, I just kind of did some of the operations. Addition works the same way, multiplication works the same way. So what about composition of functions? What is composition of functions? So composition of functions is when you combine two functions, one inside the other. Here's a little diagram. The domain of g is sort of where you start, right? Because it's f of g of x. So g of x is the inside function. So the x's that you're putting in have to be in the domain of g. And then those get taken to the range of g, but the range of g, then because I'm doing f of g of x, the range of g has to be part of the domain of f in order for f to be able to pick that value and create an output. And so that's kind of what this diagram is expressing. So essentially what we're saying is that the domain of f of g is the set of all x in the domain of g, such that g of x is in the domain of f. So that's what I'm saying. The range of g has to be in the domain of f in order for f to pick it up. A simple example that comes to mind is when you go to the grocery store and you see produce, for example, fruit, that is, the cost of the fruit is given by how much it weighs, like the watermelon, right? You get charged per pound and things like that. So we can say that g is a function that maps the fruit to its weight. And then f is a function that takes the weight of something and gives its cost. then f of g of x will give us the cost of the fruit. So that's kind of how it's working, right? So that's what I mean by the range of g. So what's being mapped here, the blue, the range of g has to coincide with the domain of f in order for f to pick it up. So fruit, g takes the fruit to its weight. So that's like you pick up the watermelon, put it on the scale. Right? That's your g function. And then once you know the weight, there's the label at the grocery store that tells you the weight, the cost based on the weight of the fruit. So if you bought a watermelon, right, then you pick it up, weigh it, so that's your G, and then the little sign on the watermelon box that tells you how much it costs per pound. Then that gives you the whole cost of the fruit. So that's a kind of real life example of composition of functions. If you can think of other nice examples of composition of functions, please send them my way. All right, so let's try an example with our functions, finding compositions of functions and finding the domain. All right, so let's try this one. Let f of x be the square root of x and g of x be x squared minus 3. Determine the following composite functions and give their domain. One of the things that I would want you to first pay attention to is the domain of each of the functions individually. So the domain of f would be, notice that we have a square root, so the domain is 0 to infinity, right? You can't take the square root of a negative number. And g of x is a polynomial, so the domain of g is all real numbers. Okay, so determine the following compositions of functions. So f circle g, so that means f of g of x. And g circle f means g of f of x. If you find the little circle notation confusing, you can always just change it to the more traditional f of functions or notation. So f of g of x. So that means into f, we're going to plug in g of x. So g of x is the inside function. So we're going to say, in this case, f, so the square root of x. So this is going to be the square root of g of x. And then substitute your g of x. So it's the square root of x squared minus 3. And so I have f of g of x is the square root of x squared minus 3. How do I find the domain? I have a radical. So that means we want the inside, the x squared minus 3, to be positive or 0. So we want x squared minus 3 to be greater than or equal to 0. If you watch my previous video about solving higher order inequalities, that's going to apply here. So this now 3 is not a perfect square. There was 4, 9, 25, 49, any perfect square, then I can factor it, but I can still say the square root of 3 squared is 3, right? So I can still write it as a perfect square. So then this is going to be x minus root 3 and x plus root 3. Even if it's not a nice perfect square, I can still do this. And we're going to do the test point method. And so I'm going to plot the zeros. So negative root 3 is what makes this term 0, and then positive root 3 makes the first term 0. And so those will be included because we can be equal to 0. And so now pick test points. So we have 3 intervals. We have from minus infinity to negative root 3 included. We have negative root 3 to root 3, both included. And the last one, root 3 to infinity. So when you pick your test points, right, we're trying to check, we want the product to be positive. So we want whatever x minus root 3 is times whatever x plus root 3 is to be positive. So that's what the greater than or equal to is telling us. We're looking for positive products. So what is negative root 3? So I know that negative root 4 is negative 2. So I'm going to pick So that gives me an idea. Okay, let's pick x equals -2 and plug it in. So I'm going to have -2 minus √3, so that's going to be a negative number, and -2 plus √3. So I have, so what is this going to be? So you may need a calculator here, but I know that's a negative number. -2 is over here, is on the left of √3, negative √3, so √3 is a smaller number, so this is still going to be negative. So I'm going to get negative times a negative is positive. Now pick something in between negative √3 and positive √3. Be nice to yourselves, choose 0. So I'm going to have 0 minus √3 and 0 plus √3. So I have a negative times a positive, so that's negative. So far, what do I have? Positive there, negative, and then what happens on this side? So pick something larger than √3, so you can pick 3 and plug it in. So you can have 3 minus √3 and 3 plus √3. So these are all positive times a positive is positive. So our domain then is going to be, we're looking for things that are positive, so the outside intervals. So now I can say the domain of, what did we have, f of g of x, which was the square root of x squared minus 3, is, and we can write our interval notation, minus infinity to negative √3 included, union positive √3 to infinity. Based on solving this inequality, I tend to use the test point method. Depending on what class you've had in the past, they may do a different method, but just make sure that you do some sort of number line of interval testing, right? The one mistake I don't want to see you fall victim of is saying, oh, x minus √3 is greater than 0, and then x plus √3 is greater than 0, and solving them individually. We are looking for the product of these two to be positive. So we don't want to look at them individually. All right, what about g of f of x? So part B, g of f of x. So that means into g, what was g? G is x squared minus 3. We plug in f of x. So that's going to be f of x squared minus 3. Right, we call g of x is x squared minus 3, and f of x is the square root of x. So I plug in my f now inside g. So that's why I have f of x squared there. And now what is f of x? Well, f of x is the square root of x, not square, minus 3, so I just get x minus 3. And what is the domain of that? This is a polynomial, so the domain is all real numbers. So recomposition of functions is really a matter of which one is the inside function. So f circle g, that means g is on the inside. G circle f, that means f is on the inside. And so when you go to, like in this case, right, f circle g, f of g of x, I take my whole g of x and plug it in for every x into f. And that's our composition. Now, other things that we may encounter are finding composition values given the graph. So let's try an example like that. All right, so let's look at this example. Use the graphs of f and g shown to find the values. So I want to find, for part A, f of g of 5. So that means I'm going to look for the inside first. So we're going to look for g of 5. So that means I'm going to go to 5. So here's my x equals 5. And let's see, the red one is g and the black one is f. So g of 5 is going to be this value right there. So that's, what is that? So I can say that g of 5 is equal to 1. And so now you take that and then you will say essentially f of g of 5. So this is, now we're looking for f of 1. So now I'm going to go to 1, like this one, and now I'm going to go to f. So that's the value of 6. So that means that this is equal to 6. So therefore, f of g of 5 is 6. So how about you try that with g of f of 3. So try it on your own, pause the video, and try to find it on your own. What did you get? Hopefully you got 1. So for g of f of 3, we look at f of 3 first. So 3, and then go to f, so that's 5. So we're really finding g of 5, which we already found in part A, right? G of 5 was 1. Now f of g of 3, so I'm going to go to 3 and now find g. So g of f of, g of f of 3. So wait, f of g of 3. Got mixed up looking at all those numbers there. So g of 3, so g3 and then g. So it's 4. So that means that I'm going to have g of 3 is equal to 4. Therefore, f of g of 3 means I'm looking for f of 4. So go to 4 and then find the f value, and that's 8. And so that means that f of g of 3 is equal to 8. And now what about g of 2? So now this is a double composition of the same function. So I'm still going to find g of 2. So what is g of 2? So let's go to 2 and go for g. So 3. So g of 2 is 3. So that means that g of 2 is really what? G of 3. And what is g of 3? We found it in the previous one. G of 3 was 4. So therefore, g of 2 is 4. Cool. So that's how you find compositions. If this was a graph and it wanted us to find f of 2 plus g of 6, then we could do the same thing, right? F of 2, and then find it, and then g of 6, find it, and then add those values. All right, email me if you have any questions.